Alright, so we are working on the problem with the dog in the sled with this person pulling it. And it says that we've got this child pulls a 15-kilogram sled with a 5-kilogram dog. And it's a horizontal surface, straight path, exerts a force of 55 newtons on the sled at an angle of 20 degrees. And we have friction, which is 0.22. That's the coefficient. So that's like how rough the surface is. We know that how rough the surface is, if this surface gets rougher, this gets higher because it creates more of a backwards force. So what the first thing it wants us to do is draw a free body diagram. And after we draw this, we will not touch it ever, ever, ever again. So the first thing that we know is we always have this normal with a surface. If we don't have a surface, we don't have normal. Then we've got, of course, this force that this person is pulling. We're going to call it tension since it looks like a rope to me. You can just call it F if you want to. But we also have got our mg, and this mg is going to be of the dog and the sled, at least for now. And then we've got this frictional force going to the left because we see that this person is moving along to the right, and friction opposes that motion, so it must be to the left. So the first thing that it wants us to do is calculate the normal force of the surface on the system. So we are not going to touch this again. So the first thing we should do is let's just draw another free body diagram. So we've got our normal, our tension, which we see is in diagonal, so it's not only in the x, it's also in the y, our friction, and our mg. We see that our normal is in the y direction, and it doesn't say anything about the sled going up or down, or it's just going straight across. So we know that our acceleration in the y direction, is going to be 0 because it's not accelerating up or down. So the sum of the forces in the y direction, the reason why we're doing that is because normal is in the y direction, it's going to equal 0. And so we've got our normal force, we've got our mg, and we're subtracting because they're going opposite directions, but we can't forget about this tension right here because this tension is not only in the x, it is also in the y direction, like that. And so this is going to be our t of y, and we see that it has an opposite relationship with that theta. And so to find that out, so we're going to use sine because it's opposite. We have got t of y because that's opposite all over hypotenuse, which is our t. And so multiply both sides by t. You get our t of y equals t sine theta. And that's what we're going to be adding right here because it's also going up. So our t of y, and so we get 0 equals normal minus mg plus t sine theta. We're looking for normal, so let's add our mg, subtract our t sine theta from both sides. So we end up with normal equaling mg minus t sine theta. Now all we need to do is plug in because they give us everything. So the normal equals our mass, which is going to be the 15 plus 5, so we get the 20 times our 10 minus the 55, because that's what they give us as the force, times the sine of 20. And we put all that together in our calculator, we should get about 1.2 newtons. All right? So now it wants to know what is the acceleration on the system. So we see that the only acceleration occurring is going to the right, okay? Because the sled's not going up, it's not going down. It's just kind of, it's staying there, but it's going to the right like that. So our acceleration is going to the right. So let's again draw another free body diagram. And so we've got our normal, our mg, our frictional force, our tension, and so this time we're looking at the sum of the forces in the x, and we actually do have an acceleration because that's what they want. They're looking for that acceleration. So we're going to say x equals ma, and then the forces in the x direction, which we see is going to be this t in the x and the friction. So we've got our t of x, and we're subtracting it from that friction right there. And our t of x has an adjacent relationship with that angle. So we're going to say cosine theta equals adjacent, which is t of x, over hypotenuse. Solving for t of x, we get t of x to equal t cosine theta. So let's plug that in. MA equals t cosine theta minus f. And so another thing that we know is that friction is equal to mu times normal. And so basically they've set us up in this problem because they've already had us solve for that normal force. And so let's just divide both sides by m. And then A equals t cosine theta minus this mu times normal divided by m. And now we just need to plug in. So A is equal to 55 cosine 20 minus 0.22 times 1.2 divided by our mass, which is going to be 20. And so we end up with, we put this in our calculator, 2.6 meters per second squared. And that's how you do that part. Now, the next part, at some time later, the dog rolls off the sled. So we lose 5 kilograms. But the child continues to pull with the same force. So basically, when we lose this mass, so we know that the sum of the forces equals MA. When we lose some of this mass, when this mass decreases and force stays the same, our acceleration is going to increase. So what does that look like on our velocity versus time graph? So in the beginning, we've got this kind of normal velocity, which we calculated to be the 2.6, and then at this time, TR, I'm guessing for the time of roll, our velocity is going to increase, and it's going to just be a straight line, and it doesn't look like super straight, but it just has a greater slope because your acceleration is going to increase right there. So this is a straight diagonal line showing we have some acceleration, but as soon as that dog rolls off, our acceleration is going to be greater, so therefore our slope is going to be greater as well.